The Davisson Germer experiment. In this video, we'll be looking at the wave behaviour of particles and the Davisson Germer experiment that looked at the diffraction of electrons. There's a lot of balance and symmetry in nature, and de Broglie postulated that if photons can behave as particles, particles can behave as waves. So with the equation on the screen, the wavelength of a particle can be found by dividing Planck's constant by the momentum of the particle. Now notice Planck's constant is very small, being to the power of -34. This means that any objects that have large momentum will have a very small wavelength. Now, in order to observe if particles do have wavelength, the particles that we have to observe are required to be very small. And this has been done through experiment. So previously we've looked at the situation on the left here, where photons have diffracted through a double slit and behaved as waves. And the interference that is produced is captured with this image here. Now, we can also use the double slit and look at smaller particles, including electrons and protons, and observe a similar behavior, where you have an interference pattern on the screen that is comprised of where the location of those small particles hit. And as there is bright spots and dark spots, this indicates that those particles behaved as waves. So William and Lawrence Bragg first produced X-ray diffraction pattern by reflecting a beam of X-rays off the surface of a crystal. So this is just particles of light hitting the surface of a crystal now, instead of a double slit or diffraction grating. What was observed was still the interference pattern. However, in this case, a two-dimensional diffraction pattern was observed. With the X-ray hitting the lattice, upon reflection, the X-rays reflect from different levels of the lattice and interfere with each other to produce these patterns. Now, one of the first experiments to try this instead of with light, but with particles, was the Davisson Germer experiment. Now, what they decided to do is test de Broglie's theory, which is that particles can behave as waves, by performing an experiment similar to the X-ray experiment. And what they did was to fire a beam of electrons at a nickel crystal lattice and observe the interference pattern that was reflected off the lattice. Due to the small spacing in the crystals and the comparative wavelength of the particles, diffraction occurred upon reflection, and it was actually found in this scenario that a bright spot, or maxima, was recorded at an angle of 50 degrees from the incident beam. Using the equation for interference as we have done previously, and the results of the X-ray experiment on the nickel lattice, the spacing between the nickel atoms was found, and the angle of the first order maximum was also found when electrons were used in the experiment. Davisson Germer could calculate the wavelength of the electrons that were fired at 54 electron volts. And what they found was that this was actually extremely close to the theoretical value as proposed by de Broglie using this equation, where the wavelength was Planck's constant divided by the momentum of the electrons. So taking into account the experimental errors, the Davisson Germer experiment supported de Broglie's theory that particles behave as waves. You can pause this slide and have a look just through the calculations of what I've got up here. In the first part, the experimental wavelength of the electrons was found. And in the second part, this was compared to de Broglie's theory, and you can see the two values of 1.65 and 1.66 times 10 to the negative 10 meters for the wavelength of electrons is very comparable, supporting this theory. Without writing an essay, list 3 points that you would discuss when considering the diffraction of a person when they walk through a doorway.